Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast expanse of our cosmos, trillions of particles pass through your body every second, completely undetected and unfelt. These ghostly travelers, neutrinos, are among the most abundant yet mysterious particles in existence. Born in the nuclear furnaces of stars, violent cosmic explosions, and even Earth's atmosphere, these nearly massless particles carry with them stories of creation and transformation from the furthest reaches of our universe. Unlike light, which can be blocked by the thinnest sheet of material, neutrinos pass through entire planets with barely a trace of interaction. Their reluctance to engage with matter makes them both frustrating to detect and invaluable as cosmic messengers, carrying untainted information across billions of light years. The pursuit of these ghost particles began in the 1930s, when physicist Wolfgang Pauli first proposed their existence, not as an exciting discovery, but rather as a desperate solution to a troubling problem: the apparent violation of energy conservation in radioactive decay. Pauli's theoretical particle was so elusive that he famously lamented, "I have done a terrible thing. I have postulated a particle that cannot be detected." Yet Pauli's impossible particle would eventually be found. In 1956, physicists Frederick Rains and Clyde Cowan positioned their detectors near a nuclear reactor at the Savannah River plant in South Carolina. There, amidst the flood of particles produced by nuclear fission, they captured the first evidence of neutrinos interacting with hydrogen atoms, producing the telltale signature of positrons and neutrons. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. What makes neutrinos so peculiar is their nature within the standard model of particle physics. They come in three known flavors: electron, muon, and tau neutrinos, named after their charged lepton cousins. But unlike other fundamental particles, neutrinos have the curious ability to change their identity as they travel, oscillating between these three flavors in a quantum dance that challenged our understanding of particle physics. This phenomenon, called neutrino oscillation, led to one of the greatest physics breakthroughs of recent decades. The detection of these flavor changes solved the decades-old solar neutrino problem, the puzzling deficit in neutrinos detected from the Sun compared to theoretical predictions. This discovery, confirmed by experiments like Super Kamiokande in Japan and SNO, Sudbury Neutrino Observatory in Canada, proved that neutrinos must have mass, contradicting the original standard model. Even with this discovery, neutrinos remain deeply mysterious. Their exact masses are unknown, with upper limits suggesting they're at least 1,000,000 times lighter than electrons. We still don't know whether neutrinos are their own antiparticles, a property that would make them fundamentally different from most other matter particles, and tantalizing hints of a possible fourth sterile neutrino linger at the edges of our experimental reach. As we enter the 21st century, neutrino astronomy has emerged as a powerful new window into the cosmos. Massive detectors buried deep underground or under polar ice now serve as our eyes and ears for these elusive messengers, allowing us to probe phenomena invisible to traditional telescopes. From the nuclear fusion powering our sun to the most violent cosmic cataclysms, neutrinos are beginning to reveal the universe in ways never before possible. To catch a ghost, you need extraordinary traps. Neutrino detectors represent some of humanity's most ambitious scientific instruments, combining massive scales with exquisite sensitivity. Unlike conventional telescopes that point skyward, neutrino observatories often look downward, using Earth itself as a filter against cosmic radiation. Deep beneath the Japanese mountains lies Super Kamiokande, a marvel of engineering containing 50,000 tons of ultra-pure water, surrounded by over 11,000 golden photomultiplier tubes. Each tube stands ready to detect the faint flashes of light produced when the rare neutrino interacts with water molecules. These fleeting interactions, occurring perhaps only 10 times per day, produce rings of light that reveal crucial information about the neutrino's type and direction. The ICE Cube Neutrino Observatory takes a different approach. Embedded within a cubic kilometer of Antarctic ice, this detector uses the frozen continent itself as its medium. More than 5,000 optical sensors are suspended on 86 strings drilled nearly 2.5 kilometers into the ice. Here they wait for the distinctive blue light produced when high-energy neutrinos collide with atoms in the pristine ice. Light that has been described as the Cherenkov radiation, appearing as an ethereal blue glow. The challenges of neutrino detection extend beyond their reluctance to interact with matter. Background radiation, cosmic rays, radioactive decay, and even atmospheric neutrinos creates noise that threatens to drown out the signal. This is why these detectors are placed in such extreme locations, beneath mountains, deep underground in abandoned mines, or under the Antarctic ice. Earth itself becomes the shield against unwanted particles. The Sudbury Neutrino Observatory in Canada used an innovative approach with heavy water containing deuterium rather than ordinary hydrogen. This allowed scientists to detect all 3 neutrino flavors simultaneously, leading to the groundbreaking discovery of neutrino oscillation. The experiment's success earned Arthur MacDonald the 2015 Nobel Prize in Physics, shared with Takaaki Kajita from Super Kamiokande. The sheer scale of these instruments reflects the elusiveness of their quarry. The newest generation of detectors includes the Deep Underground Neutrino Experiment, DUNE, which will use 70,000 tons of liquid argon to study neutrinos fired through Earth's crust from Fermilab near Chicago to the Sanford Underground Research Facility in South Dakota, a distance of 1,300 kilometers. What makes these detectors so remarkable is their dual nature. Though built primarily to study neutrinos themselves, they have evolved into multi-messenger observatories, capable of detecting neutrinos from diverse cosmic sources. When supernova 1987A exploded in the Large Magellanic Cloud, 3 neutrino detectors around the world captured a burst of neutrinos hours before visible light from the explosion reached Earth, marking the birth of neutrino astronomy. These technological marvels represent the culmination of decades of innovation, pushing the boundaries of materials science, electronics, and computing. The photomultiplier tubes in Super Kamiokande can detect single photons. ICE Cube's optical modules must function flawlessly for decades in the crushing pressure and sub-zero temperatures of Antarctic ice. The electronics must distinguish the faint signatures of neutrino interactions from the continuous background of cosmic rays and natural radioactivity. As our detectors grow more sophisticated, so too does our ability to peek into the hidden corners of the universe. Each technical advancement brings us closer to answering fundamental questions about these ghost particles and the cosmos they traverse. Every second, our sun produces an astounding number of neutrinos, approximately 100 billion, 10 to the power of 26. This immense neutrino flux emerges from the thermonuclear fusion reactions powering our star. In the sun's core, where temperatures reach 15 million degrees Celsius, protons fuse to form helium, releasing energy and electron neutrinos in a process known as the proton-proton chain. These solar neutrinos stream outward at nearly the speed of light, reaching Earth just 8 minutes after their creation. The detection of solar neutrinos provided crucial validation of our models of stellar evolution. In the 1960s, Raymond Davis Jr. established the first solar neutrino detector, a tank containing 600,000 liters of perchloroethylene, dry cleaning fluid, buried deep within the Homestake gold mine in South Dakota. The chlorine atoms in this fluid would occasionally capture a neutrino and transform into an isotope of argon, which could then be counted. For decades, Davis meticulously extracted and counted these argon atoms, sometimes just 15 per month. But a puzzle emerged. Davis was detecting only about 1/3 of the neutrinos predicted by solar models. This solar neutrino problem persisted for nearly 30 years until the discovery of neutrino oscillations provided the solution. The missing neutrinos weren't absent. They had simply changed identity during their journey from the Sun to Earth, transforming from electron neutrinos into muon and tau varieties that the early detectors couldn't observe. Stars much larger than our Sun contribute differently to the cosmic neutrino population. During their normal lives, massive stars generate neutrinos through more complex nuclear reactions, but their most significant contribution comes at death. When a massive star exhausts its nuclear fuel, its core collapses under gravity's pull. This catastrophic implosion creates conditions of extreme temperature and density, triggering a supernova explosion that can briefly outshine an entire galaxy. In just a few seconds, a supernova releases an astonishing burst of neutrinos carrying 99% of the explosion's energy. Approximately 100 billion neutrinos flood outward, most escaping hours before the visible light emerges. This neutrino burst serves as the earliest warning system for supernovae, and detecting such signals allows astronomers to quickly direct conventional telescopes toward these cosmic explosions. The first, and so far only, detection of supernova neutrinos occurred on February 23, 1987, when observers spotted a blue supergiant star exploding in the Large Magellanic Cloud, a satellite galaxy of our Milky Way. 3 neutrino detectors, Kamiokande 2 in Japan, IMB, Irvine, Michigan, Brookhaven in the United States, and Baksan in the Soviet Union, detected a total of 25 neutrinos from this explosion, designated SN 1987A. These neutrinos had traveled approximately 168,000 light-years to reach Earth, arriving 3 hours before the first visible light was observed. This seemingly counterintuitive timing actually confirms our understanding of supernova physics. Neutrinos escape almost immediately from the collapsing core, while light must navigate through the dense outer layers of the exploding star. Beyond. Stars, even more exotic cosmic phenomena, produce neutrinos. When supermassive black holes at galactic centers actively consume matter, the resulting accretion disks and jets can accelerate particles to nearly the speed of light. These high-energy environments generate neutrinos that can reach energies millions of times higher than those produced in our most powerful particle accelerators. In 2013, ICE-Cube detected the first ultra-high-energy neutrinos from beyond our galaxy, opening a new frontier in multi-messenger astronomy. The cosmic landscape of neutrino sources continues to expand as our detection capabilities improve. From the continuous fusion in stellar cores to the violent deaths of massive stars, from active galactic nuclei to potential dark matter interactions, neutrinos offer unique insight into the most energetic processes in our universe, processes often hidden from traditional observation methods. While cosmic neutrinos journey across vast interstellar distances, Earth itself generates its own substantial neutrino population. These terrestrial neutrinos come from both natural and human-made sources, creating a complex background that scientists must carefully account for in their search for distant cosmic signals. Our planet's most significant natural neutrino source lies deep within the crust and mantle. Radioactive isotopes of uranium, thorium and potassium, remnants from Earth's formation nearly 4.5 billion years ago, undergo decay processes that release heat and produce electron antineutrinos. These geoneutrinos emerge from Earth's interior at a rate of millions per square centimeter per second, carrying with them information about our planet's composition and internal heat budget. The Camland detector in Japan and the Borexino detector in Italy have successfully measured these geoneutrinos, confirming that approximately half of Earth's internal heat comes from radioactive decay, a crucial discovery for understanding our planet's thermal evolution. The remaining heat is primordial, left over from Earth's formation, and the gravitational energy released during core differentiation. Earth's atmosphere serves as another natural neutrino factory. When high-energy cosmic rays, mostly protons, accelerated by distant supernova, collide with atoms in the upper atmosphere, they trigger particle cascades that include pions and muons. As these unstable particles decay, they produce neutrinos of various flavors. These atmospheric neutrinos arrive from all directions and span a wide energy range, creating a natural laboratory for studying neutrino properties. It was through careful measurement of atmospheric neutrinos that the Super Kamiokande experiment first definitively proved neutrino oscillation in 1998. Scientists observed that fewer muon neutrinos arrived from the far side of Earth, having traveled through the planet, than from above, evidence that some had transformed during their journey through Earth's diameter. Human activity contributes significantly to Earth's neutrino production. Nuclear reactors are particularly prolific sources, with each reactor producing approximately 10 to the power of 20 antineutrinos per second during operation. These reactor neutrinos emerge from the beta decay of neutron-rich fragments produced by uranium fission. Their well-defined energy range and predictable flux make them valuable tools for studying neutrino properties. The first experimental detection of neutrinos used a reactor source, and today experiments like Daya Bay in China, Reno in South Korea, and Double Choose in France continue to use reactor neutrinos to investigate oscillation parameters and search for potential new physics. These experiments have precisely measured the mixing angle θ13, completing our understanding of how neutrinos transform between flavors. Particle accelerator facilities also generate neutrinos by accelerating protons and smashing them into targets. The resulting particle showers include pions and kaons that decay into well-controlled beams of neutrinos. Unlike reactor or natural sources, accelerator neutrinos can be produced with specific flavors, typically muon neutrinos, and directed toward distant detectors. Experiments like T2K in Japan, NOVA in the United States, and the upcoming DUNE project use these beams to precisely study oscillation properties and search for CP violation, an asymmetry between matter and antimatter that might help explain the universe's matter dominance. Even the human body contains natural radioactive potassium-40, making each of us a source of neutrinos. A typical adult human emits about 340 million neutrinos per day through this natural radioactivity. Collectively, Earth's 8 billion humans contribute a tiny but measurable fraction to the planet's overall neutrino budget. This diverse array of terrestrial sources creates a complex neutrino background that must be carefully characterized. For scientists hunting rarer signals, whether from distant galaxies or exotic physics, understanding these local contributions is essential for distinguishing the extraordinary from the ordinary. In the emerging field of multi-messenger astronomy, neutrinos stand apart from other cosmic messengers for one remarkable reason. They travel through the universe virtually unimpeded. Unlike light, which can be absorbed, scattered, or blocked by matter, neutrinos pass through gas clouds, planets, and even entire galaxies with almost no interaction. This ghostly quality makes them unique witnesses to cosmic processes hidden from traditional observation. The universe is largely transparent to neutrinos. A neutrino could traverse a light-year of lead, more than 9 trillion kilometers of solid metal, and still have a reasonable chance of passing through untouched. This extraordinary penetrating power allows neutrinos to escape from environments where photons remain trapped for thousands or even millions of years. In our sun's core, for example, light might take 100,000 years to reach the surface through countless absorptions and re-emissions, while neutrinos escape directly in just 2 seconds. This property proves particularly valuable for studying dense, energetic cosmic environments. The collapsing cores of dying massive stars are so dense that even light cannot escape directly. As these stellar cores implode to form neutron stars or black holes, temperatures reach tens of billions of degrees Celsius, and densities approach that of atomic nuclei. Under these extreme conditions, neutrino production skyrockets, carrying away vast amounts of energy and information about the collapse process. When observed alongside electromagnetic radiation, gravitational waves, and cosmic rays, neutrinos offer a complementary perspective that helps complete our cosmic picture. This multi-messenger approach reached a milestone in 2017 when the ICE Cube Observatory detected a high-energy neutrino from the direction of a blazar designated TXS 0506 plus 056, an active galaxy with a relativistic jet pointed toward Earth. Follow-up observations by more than 20 observatories across the electromagnetic spectrum confirmed this galaxy as the neutrino source, marking the first confirmed cosmic neutrino source beyond our solar system. Neutrinos also serve as time capsules from the early universe. Cosmic microwave background photons, often described as the oldest light in the universe, provide a snapshot from 380,000 years after the Big Bang, when the universe became transparent to light. But a cosmic neutrino background should exist from a much earlier epoch, just 1 second after the Big Bang, when the universe cooled enough for neutrinos to decouple from other matter. These primordial neutrinos, now greatly redshifted and difficult to detect, would offer unprecedented insight into the universe's earliest moments. The directional nature of neutrino detection adds another valuable dimension. When a neutrino interacts in a detector like Super Kamiokande or ICE Cube, scientists can determine not just its energy, but also its arrival direction, allowing them to point back toward its source. This capability transforms neutrino detectors into true astronomical instruments, telescopes for the invisible. Neutrino astronomy extends our observational reach to phenomena completely hidden from light-based astronomy. The nuclear fusion processes occurring in stellar cores become directly observable. The moment of core collapse in a supernova becomes detectable hours before any visible indication, and the acceleration mechanisms in active galactic nuclei can be probed directly through the high-energy neutrinos they produce. As we build larger, more sensitive detectors, the range of observable sources grows. The next generation of neutrino telescopes, including KM3net in the Mediterranean Sea, Baikal GVD in Russia's Lake Baikal, and ICE Cube Gen 2 in Antarctica, will vastly expand our neutrino sky map, potentially revealing new classes of cosmic accelerators and shedding light on the origin of the highest energy cosmic rays. Where traditional astronomy has mapped the universe through light collected by increasingly sophisticated telescopes, neutrino astronomy peers into regions forever hidden from electromagnetic observation, revealing the universe's most energetic and densely packed environments through the ghostly particles that freely escape them. Neutrinos occupy a unique and puzzling position within the standard model of particle physics. First proposed as massless particles with distinct flavors, electron, muon, and tau, neutrinos have consistently surprised physicists, challenging our fundamental understanding of nature's building blocks and pointing toward physics beyond our current theoretical framework. The discovery of neutrino oscillation in the late 1990s and early 2000s triggered a revolution in particle physics. These flavor transformations, where neutrinos change identity as they travel, provided definitive proof that neutrinos possess mass, contradicting the Standard Model's original formulation. This discovery earned the 2015 Nobel Prize in Physics and opened a pathway to exploring physics beyond our established theories. The mass hierarchy of neutrinos remains one of particle physics' great unsolved puzzles. While we know neutrinos have mass, their exact masses remain unknown. Experiments have established only upper limits and the differences between mass states, suggesting neutrinos are at least 1,000,000 times lighter than electrons. This extreme lightness raises profound questions. Why are neutrinos so much less massive than other fermions? Does their mass originate through the same Higgs mechanism as other particles, or through some entirely different process? One intriguing possibility is the seesaw mechanism, which proposes that each known neutrino has an extremely heavy partner particle. Through quantum mechanics, the extreme heaviness of these hypothetical particles would explain the extraordinary lightness of the neutrinos we observe. If confirmed, this would connect neutrino physics to energy scales approaching those of grand unified theories, potentially explaining other mysteries like the matter-antimatter asymmetry of our universe. Neutrinos might also help resolve one of physics' greatest questions. Are neutrinos their own antiparticles? Most matter particles are distinct from their antimatter counterparts, but neutrinos could be Majorana particles, identical to their antiparticles. Experiments searching for neutrinoless double beta decay, a rare nuclear process possible only if neutrinos are Majorana particles, may soon answer this fundamental question about neutrino nature. The search for additional neutrino types beyond the three known flavors continues to intrigue physicists. Several experiments have reported anomalies suggesting the existence of sterile neutrinos that don't interact through any fundamental force except gravity. The LSND and Mini-Boon experiments both observed excess neutrino events that could indicate sterile neutrinos with masses around 1 electron volt. More recently, the Microboon experiment has called these results into question, highlighting the experimental challenges in this frontier area of research. Cosmology places important constraints on neutrino properties. The total mass of all neutrino types affects how matter clustered in the early universe, leaving subtle imprints on the cosmic microwave background and large-scale structure. The Planck satellite data suggests the sum of neutrino masses must be less than 1/10 of an electron volt, much lighter than any other known massive particle. Neutrinos may even connect to the mystery of dark matter. While standard neutrinos move too quickly to account for dark matter, theoretical extensions like sterile neutrinos remain viable dark matter candidates in some mass ranges. These particles would have been produced in the early universe and, unlike regular neutrinos, would not be tied to specific sources we can monitor. The study of neutrinos has consistently revealed gaps in our understanding of fundamental physics. From oscillations that prove they have mass to potential connections with dark matter and the matter-antimatter asymmetry, neutrinos stand at the intersection of particle physics, cosmology, and astrophysics. Their peculiar properties suggest they might hold clues to some of science's most profound questions. As experiments grow more precise, our understanding of these ghost particles continues to evolve. The Katrin experiment in Germany is directly measuring the electron neutrino mass with unprecedented precision. T2K in Japan, NOVA in the United States, and the upcoming DUNE facility are probing whether neutrinos and antineutrinos oscillate differently, a form of charge parity violation that could help explain why our universe contains matter but very little antimatter. Each new measurement brings us closer to understanding not just neutrinos themselves, but the fundamental structure of matter, energy, space, and time. As we look to the horizon of neutrino science, a new generation of experiments promises to transform our understanding of these elusive particles and the universe they inhabit. These ambitious projects, some under construction, others in planning, will push technological boundaries to address the most compelling questions in neutrino physics and astronomy. The Deep Underground Neutrino Experiment, DUNE, represents one of the most ambitious scientific endeavors of the 21st century. Located deep beneath the hills of South Dakota at the Sanford Underground Research Facility, DUNE will use 70,000 tons of liquid argon to detect neutrinos fired from Fermilab near Chicago, a distance of 1,300 kilometers. This unprecedented experiment will measure neutrino oscillations with extraordinary precision, potentially revealing whether neutrinos and antineutrinos behave differently, a form of charge parity violation that could help explain the matter-antimatter asymmetry of our universe. In the Mediterranean Sea, KM3NET is deploying thousands of optical modules across multiple cubic kilometers of seawater. This next-generation neutrino telescope will search for high-energy neutrinos from distant cosmic sources, complementing the ICE Cube Observatory at the South Pole and providing crucial coverage of the Northern Hemisphere sky. Together with Baikal GVD in Russia's Lake Baikal and the planned ICE Cube Gen 2 expansion, these instruments will form a global network of neutrino observatories with unprecedented sensitivity to cosmic neutrino sources. Japan's Hyper Kamiokande detector, scheduled to begin operation in 2027, will contain 260,000 tons of ultra-pure water, 8 times the volume of its predecessor, Super Kamiokande. With 40,000 photomultiplier tubes, this massive detector will study neutrinos from accelerators, the atmosphere, the sun, and supernovae with extraordinary precision. If a supernova explosion occurs in our galaxy during its operation, Hyper-Kamiokande could detect up to 100,000 neutrinos from the event, providing unprecedented insight into the explosion mechanics. The search for neutrinoless double beta decay, a theoretical nuclear process that would prove neutrinos are their own antiparticles, continues with increasingly sensitive experiments. Projects like Legend, Nexo, and Cupid are scaling up to ton-scale detector masses, pushing measurement sensitivities to previously unreachable levels. A positive detection would revolutionize our understanding of neutrino nature and potentially explain how matter came to dominate over antimatter in our universe. Direct measurements of neutrino mass continue to improve. The Katrin experiment in Germany has already placed the most stringent upper limit on the electron neutrino mass and will continue refining this measurement. Meanwhile, cosmological observations from missions like the Euclid satellite and the upcoming Vera Rubin Observatory will constrain the sum of neutrino masses through their gravitational effects on large-scale cosmic structures. Perhaps most exciting is the prospect of detecting the cosmic neutrino background, relic neutrinos, from just 1 second after the Big Bang. Projects like Ptolemy aim to capture these extremely low-energy neutrinos, which would provide our earliest possible window into the universe's history. Success would represent a breakthrough comparable to the first detection of the cosmic microwave background, potentially revealing new physics from the universe's earliest moments. The integration of neutrino detectors into multi-messenger observation networks continues to advance. When gravitational wave observatories like LIGO, Virgo, and Cagra detect a merger event, or when gamma-ray satellites spot a high-energy burst, neutrino observatories can quickly search their data for coincident signals, potentially revealing the inner workings of these energetic cosmic events in unprecedented detail. Applications beyond fundamental science are emerging as well. Neutrino detectors have demonstrated potential for monitoring nuclear reactors from a distance, supporting non-proliferation efforts by detecting the operation of undeclared nuclear facilities. Geoneutrino measurements continue to improve our understanding of Earth's internal heat budget and composition, and the technology developed for neutrino detection finds applications in fields ranging from medical imaging to national security. As we peer beyond the current experimental horizon, neutrino science stands at the confluence of particle physics, astrophysics, cosmology, and technology. These ghost particles, once thought undetectable, now serve as messengers from the cosmos and windows into fundamental physics. With each new detector and each new detection, we move closer to understanding not just neutrinos themselves, but the universe they traverse and the laws that govern it. The journey that began with Wolfgang Pauli's desperate hypothesis continues, today, driven by human curiosity and ingenuity, a testament to our enduring quest to understand the most elusive aspects of our universe.